All right, let's get started. So today we're going to start on some of the more advanced topics leading up to discussion next week on inverse reinforcement learning. But before we do that, a few logistical notes. So homework 3 is actually due today, so by 11:59 p.m. tonight, please make sure that you turn in your homework 3. And then homework 4 will come out tonight. So I think it should actually already be posted on the website, but officially everything should be out by tonight, and that's the last homework. It's actually going to be on model-based reinforcement learning, and then after that, you'll have the rest of the semester to work on your final projects. And speaking of final projects, the final project proposal is actually due on Monday, so this has been on the course website for quite a while, but it's coming up, so make sure that you get your project proposal written up and turned in on time, usual time, 11:59 p.m. Monday night. If you have any questions or concerns, or you want to bounce around some ideas for your final project, please do come to the office hours. You can talk to the GSIs in today's office hours. You can talk to me on Friday. My office hours this Friday are at a slightly different time, so I posted that on Piazza. It's going to be, I think, at 10:30 a.m. instead of the usual 9 a.m. time, so just check on Piazza if you're signed up for my office hours on Friday. Okay, today's lecture. So today, we're going to shift gears a little bit. So far, we've talked mainly about how we can develop algorithms for enabling machines to make good decisions to optimize reward functions. And we'll actually talk about that today too, but we'll gradually transition into also talking about how optimal decision making can serve as a model of observed expert behavior, observed human behavior. So today we'll talk about both modeling observed behavior and automatically making decisions. And then next week we'll talk about inverse reinforcement learning, which is primarily concerned just with modeling observed behavior to recover objective functions. So today we're going to talk about some probabilistic models that we can use to reason about observed behavior and also develop interesting new reinforcement learning algorithms. And then next week we'll talk about how those models can be used to infer reward functions from observations. So we'll talk about, does reinforcement learning and optimal control actually provide a reasonable model of observed human behavior? We'll talk about, if it doesn't, I'll give away the punchline. It doesn't quite, but there is a better explanation. And to derive that better explanation, we'll look at a connection between optimal control, reinforcement learning, and probabilistic inference. So we'll actually see how we can build probabilistic graphical models where inference looks very similar to reinforcement learning and optimal control. And then this will induce a small change in some of our RL algorithms. So we'll see that many of the same reinforcement learning tools we learned so far can still be applied, but they look a little bit different, and we get slightly different answers. And we'll discuss some of the implications of that. And then next week, we'll see how this is actually a crucial ingredient for inverse reinforcement learning. So the goals for today will be to understand the connection between probabilistic inference and optimal control, understand how specific reinforcement learning algorithms can be instantiated in this control as inference framework and how they change when you do that, and then understand why this might actually be a good idea. So why should we care about this stuff, and why might it be an interesting avenue to produce better reinforcement learning methods? All right, so let's think a little bit about human behavior. So there's been, obviously a huge volume of work in the literature on studying things like human locomotion, navigating around in a room, reaching, and even higher level navigation, like how do you choose which path to drive around a city if you want to get from one location to another in your car, right? Now, a reasonable hypothesis about human behavior is that if a person is trying to achieve some goal, perhaps what they're doing looks a little bit like planning or optimal control. So they understand that they have some kind of goal they want to reach, some kind of reward function. The world is governed by some dynamics or physics, and they'd like to achieve their goal with respect to their understanding of the dynamics model. So the formalism of optimal control that we learned about previously might be a good formalism to think about this. Maybe we imagine that, if this guy's trying to run over here, perhaps he has a model of physics of his own dynamics, and he's trying to maximize some reward, like running at a particular speed. If you're trying to navigate the city over here, perhaps you understand the dynamics, which in this case is the connectivity of the roads, and you'd like to maximize your reward, which might correspond to reaching your destination as soon as possible. So you wouldn't want to intentionally drive around in a circle. You want to take the most direct path. And maybe in a stochastic case, same deal. Perhaps you're maximizing your policy to maximize your expected reward, subject to some constraint on your dynamics and so on. Quite a reasonable model, if we say that, well, if people are rational, maybe they behave more or less optimally. So you might say, well, perhaps if we want to study how a person does something, if we can find their reward function, maybe the framework of optimal control or reinforcement learning can give us an explanation for what kind of actions they would take in different situations. Okay, this is a reasonable hypothesis. And in fact, people have investigated this hypothesis in various settings. You can, for example, get a monkey, give that monkey a little joystick, and ask the monkey to do some task like use the joystick to control a little dot on a screen to make that dot go to a desired location. If the monkey gets the dot to the desired location, it gets a little bit of juice, and it becomes a happier monkey. So if you're a researcher and you get this monkey in your lab and you train it up to use that joystick really well, you might say, well, the dot starts over here on the screen, the monkey is told to get it over here, and you expect a really smart monkey to take a straight line path and get its juice. But a real monkey, of course, is not going to do it perfectly each time. A real monkey might take a path like this or a path like this, and it's happy enough because it still gets the juice in the end. So then you kind of wonder, well, is something wrong with the monkey? Like, why would it do the blue thing instead of the black thing? It's suboptimal. Why would it do that? The fact is that the monkey, like any animal, is not an optimal monkey. It's an approximately optimal monkey. And as far as the monkey is concerned, it gets the juice whether it does the blue thing or the black thing. So it's going to actually allocate its effort accordingly so as to produce the maximal return, but not actually work super hard to get the completely perfect answer, because the incentives are just not there for that. So some mistakes matter more than others. If it misses the target, it doesn't get the juice, then it's not happy. But if it gets to the target just in a less optimal way, maybe it takes a few milliseconds longer, the monkey doesn't really care about that. So it's not an optimal monkey, it's an approximately optimal monkey. Its behavior is stochastic, but good behavior is still the most likely, especially when the stakes are high. So it might take a circuitous path to the target, but it will put in a bit of effort to reach that target because it wants the juice. So that's maybe a little closer to how real observed human or animal behavior might look like. But there's a little complication here. What is the mathematical formalism that explains why the blue paths are OK, but like something that goes off and doesn't reach the target is not OK? Like where do we draw that boundary? How do we decide what is approximately optimal? And how do we explain why there might be this random variation in the blue lines? Well, in general, if you observe stochastic phenomena and you sort of put on your machine learning hat, one of the things that you might say is, well, let's come up with a probabilistic model such that samples from this model look like the observed stochastic phenomena. So can we come up with a probabilistic model such that when we sample from that model, we get behaviors that resemble our approximately optimal monkey? So that means that we would like to come up with a probabilistic model of decision-making. And we're going to draw a graphical model and try to figure out how that model can produce samples that look like approximately optimal behavior. So that means that we won't necessarily go with the hard optimality model that says that you should always arrive at the perfectly optimal behavior. We'll try to come up with something where suboptimal behavior also has a non-zero probability. OK, so if we're going to draw a probabilistic model for behavior, we probably need some states and actions in there. We already understand how states and actions influence next states. That's governed by the system dynamics or the transition probability. So that part we're good about. And we could say, OK, well, we care about trajectory, so we care about joint probabilities of sequences of states and actions. Those are our taus. So we can draw a model like this. We can say, P of S1 through T, A1 through T, that's a probability of seeing some trajectory, and that's equal to something. But here, there's not yet any assumption about optimal or near optimal behavior. So if we just draw this graphical model as is, that doesn't tell us anything about what the monkey is trying to accomplish. This just tells us what are the laws of physics governing the monkey. So the monkey can't fly, unless it's a flying monkey, I guess, but it can reach for stuff, right? So this can tell us, OK, reaching motions are plausible, but flying motions are extremely unlikely. But that doesn't tell us anything about the monkey's intention. So we need to add something to this model to model the monkey's intention. OK, we need to name it. Let's call it script O for optimality. There's some variable that we're going to add to the network that says, like, this is the variable that represents the monkey trying to optimally achieve some goal. And it's trying to do this at every time step, and this variable is observed. We know that the monkey is trying to be optimal. And let's just say, for the sake of simplicity, this variable is binary. It's either 0 or 1. Either the monkey is trying or it's not trying. If it's not trying, then that variable is 0, and if it is trying, it's 1. So we've sort of tacked on this little binary variable, observed binary variable, to every single time step, and it's 1 because we know that the monkey is trying to achieve its goal. And then what we're going to try to do is we're going to solve this inference problem. Find the probability of seeing a trajectory conditioned on the fact that the monkey is attempting to achieve some goal, conditioned on the optimality variables from time step 1 through capital T being true, being 1. And we need to pick how we're going to represent this distribution, the probability of O given S and A. And we're going to pick this. We're going to pick it to be proportional to the exponential of the reward. And the reason we're going to do that will become apparent very shortly. So for now, take my word for it, but you'll see very soon why it makes perfect sense to say that the probability of this variable being true is proportional to the exponential of the reward in that state in action. And you need to normalize it to actually have this be a proper distribution. Yes?
If I had drawn this graphical model, I would have had just one arrow from O to A.
Mm-hmm.
Why are there two arrows towards O? It seems like my causes doesn't fit my intuition about the causality.
Right. So the reason that we want to draw it like this is because we don't want to, so we're going to actually do inference to figure out the other thing. So the way that your A depends on O, that you need to do inference. You need to actually do some work, some planning. But your O here is an instantaneous consequence of your state in action. And one way to think about this is that if the monkey is trying to be optimal, then it has a much bigger chance of that optimality variable being 1 if it actually reached the goal. So once we go through the math for the inference procedure, I think this will become a bit more apparent. All right, so for now, let's just assume this. Let's just take my word for it. We'll do probability of O is proportional to the exponential of the reward, and let's see what happens if we do that. So if we do that, then we can write P of tau given all the O's by the definition of conditional distribution as the joint probability of tau and O divided by some normalizer. And we don't have to worry about the normalizer for now, so let's just say it's proportional, and it's proportional to this joint. And what is this joint? Well, this joint is the probability of the trajectory, so that's just the probability of that sequence of states and actions happening due to the laws of physics. So this first term, P of tau, just says, flying is unlikely, but reaching, that's perfectly fine. And then we have the product of all of these probabilities of the O's, right? Because given the S's and A's, all the O's are independent of each other, so we can just multiply them together like this. So we multiply together all of the exponential R's, and we don't care about the normalizer because we wrote this proportionality thing here. And when we multiply together a bunch of these exponentials, that's the same as the exponential of the sum of the exponents. And now, what we get is actually quite intuitive. We get this thing that says the probability of the trajectory happening due to physics times the exponential of its total reward. So that means that the most rewarding trajectory that is still physically feasible is going to be the most likely, right? So if the optimal trajectory is for the monkey to reach for that dot in a straight line, and that agrees with the laws of physics, that's going to be the most likely trajectory that you're going to get. But if there's another trajectory that has almost the same reward and is also physically possible, that trajectory is also quite likely to occur. And if you have a tie, if you have multiple trajectories that all have the same reward, and they're all physically possible, then they're all equally likely to occur. So this is a model that tells you why you might observe trajectories that are not completely perfect, but still pretty good. So if the monkey, for example, is incentivized to reach the right destination at the end of the trajectory, there will be a big reward at the end and not much reward in the middle. So that might explain why you might see a lot of variance on the way to the goal, but all those trajectories end right at the goal. And you'll randomly sample from this distribution. So the most likely behavior, so the most rewarding behavior is the most likely, and as they become less rewarding, they become exponentially less likely. So this is a model that describes why you might see suboptimal behavior. Yes?
Did you see the P of tau as being like a factor that sort of encodes like what would be, I guess the most likely trajectories like by the I guess the bias and the dynamics, and then the other term, the sum being like the bias of the actor kind of thing?
That's basically the idea. So if we'd like to understand this P of tau term, here's a thought exercise that might help. Let's imagine that our physics are very simple. There is one thing that can happen, and everything else is impossible. So this P of S prime given SA is just a bunch of Dirac deltas. Now, the P of taus are going to be always either 0 or some constant. Right? All the physically possible things have some constant probability, and all the things that are impossible have a 0 probability under P of tau. Then everything is very simple. Then this term essentially vanishes because it's a constant. If your dynamics are more complex, if they're stochastic, then what this basically says is that if there's some trajectory that's very unlikely to occur, but physically possible, you're less likely to see it because an optimal actor won't want to take that risk. And this actually agrees with how an optimal action would act under stochastic dynamics. That, you know, what you're trying to do is you're trying to maximize your reward and expectation. So if there's some path to the goal, but it's very unlikely to happen, then you're not going to take it over one that is maybe a little bit less rewarding but more likely, because an expectation your reward will be lower. Yes.
Does P of tau assume that actions are chosen uniformly at random?
So P of tau is not assuming anything about how actions are chosen. It's just looking at a trajectory and giving it a probability of occurring under the laws of physics.
But the trajectory depends on the actions, doesn't it?
Yeah, so the tau is just defined right here as a sequence of states and a sequence of actions. So P of tau just says, for this sequence of states and this sequence of actions, how likely is it to occur under the laws of physics? So if I'm driving my car and I turn the steering wheel to the left, but the car goes to the right, that is technically possible if there's some malfunction, but pretty unlikely.
So it's like less than 1/5 the dynamics are stochastic, but now we can looking at what the active is.
So this is not reasoning at all about how you might choose the action. This is just sort of critiquing a sequence of states and actions, saying, are they possible? OK, so this is the monkey. Now, why is this, you know, we went through a lot of trouble to arrive at this, and we're going to go through a lot more trouble in the rest of the lecture. But before we do that, why is this interesting? Like, why should we care about the fact that you can draw this graphical model and get this probability of trajectories that has the reward in it? Well, one of the reasons why it's interesting, which I've alluded to before, is that you can model suboptimal behavior, which ends up being very important if you want to actually do inverse reinforcement learning. If you want to look at somebody executing some behavior and try to figure out why they're doing it, you might want to be able to represent why they might do things in a slightly suboptimal way. This framework allows you to apply inference algorithms to solve control and planning problems. So now that we've formulated everything nicely in a probabilistic graphical model, the full arsenal of probabilistic inference algorithms is at our disposal to solve problems that look like control and planning problems. And it can actually provide an explanation for why stochastic behavior might actually be preferred over perfectly deterministic behavior, which can give rise to some interesting reinforcement learning algorithms that have improved exploration and improved capacity for transfer learning. And that we'll actually talk about at the end of today's lecture. So this is a little preview of why we should care about this. And we'll come back to some applications at the end. But first, let's talk about the algorithmic tools that we can use to work with these kinds of models. So this is a probabilistic graphical model. And if you want to answer questions about probabilistic graphical models, like, for example, answer the question of, you know, if you're optimal, how likely is a certain action in a particular state? That is an inference problem. So we need to be able to do inference in these models. And specifically, when we do inference, there are basically three types of questions that we need to answer, depending on the problem we're solving. The first question is, how can we compute backward messages? So backward messages, those of you that are familiar with HMMs or Kalman smoothing will recognize this. A backward message basically tells you what's the probability of your observations, your optimality variables, from now until the end of time, given your current state and action. So basically, what's the probability of the current of being optimal in the future if you're in a particular state and take a particular action? This is a little bit abstract, but we'll see why it's relevant shortly. The second question, and this one might be a little bit more obvious, is how do we compute a policy? How do we figure out what's the probability of an action given a certain state and given optimality at all of the states? So if you're optimal, if you know you're optimal everywhere and you're in a particular state, what is the probability of taking a particular action? And that's a policy. And then the third question is, how can we compute forward messages? How can we figure out what's the probability of landing in a particular state if you've been optimal at all the time steps up until now? And this will be important if we eventually want to figure out state marginals. If we want to, like, the question we'll eventually want to answer is, what's the probability of landing in a particular state if you're optimal everywhere? And it turns out that if you can get these forward messages, you're very, very close to answering that question. So in the first part of today's lecture, I'll go through these three questions, and we'll derive actually the math for how to answer these three questions. And we'll see that from answering those questions, we'll get policies that tell us how to act, and we'll actually get state marginals that tell us how likely are we to land in certain states if we're acting approximately optimally. All right, so let's start with question one, the backward messages. So the backward message, beta, gives you the probability that the optimality variables are true, or 1, at all the time steps from the current step t until the last one, capital T. So they don't care at all about the past, they just care about the present through the future. And the reason that we call them backward messages is that we can compute them, just like in LQR that we studied before, we can compute them from the back to the front of the trajectory. So we start at the back of the trajectory, where it's very easy to get a backward message, and go to the front. When you're at the very back of the trajectory, when little t is equal to capital T, can anybody tell me how we can compute the backward message? So at the last time step, it's that's right, yeah. So at the very last time step, it's P of O of capital T given S capital T, A capital T, which is exactly this thing. We already know that. So that's just proportional to the exponential of the reward. So we just plug that in and we normalize. So the backward message at the very last time step is easy. We already know it. It's just this thing. So now all we have to do is figure out how to compute backward messages at preceding time steps, given that we know the backward messages at all the future time steps. So if we know the backward message at time step t plus 1, how do we compute it at time step t? And now we'll derive that. So there'll be some math with integrals and all this other fun stuff, but it's actually not that bad. So all we do is we first plug in the state at time step t plus 1. So we want to do that because we know the backward message at time step t plus 1, so we need to start adding some of these t plus 1 terms. And the first t plus 1 term that we add is the state at time step t plus 1. Now, anytime you have a probability distribution, you can always plug in whatever variable you want and integrate it out. So if you're integrating out, you can put in whatever you want. And I'm going to choose to put in st plus 1. So that's all good. And if it's discrete, this will be a sum instead of an integral. And now we'll take this thing and we'll break it up into a product of a bunch of terms, most of which we know. So we can take this thing and we can look, oh, if we know the state t plus 1, then all the future O's are conditionally independent of all the past O's, right? The state sort of puts this break for conditional independence. So all the future O's don't depend on all the past O's if we know the state. So that's why we can break it up so that one term is just all the future optimality from t plus 1 to capital T given just the next state. Because we know that all these future O's given the next state don't depend on the current state in action, because they're conditionally dependent given the next state. Then we have the probability of the next state given the current state in action, right? Because if we multiply these two things, then we get P of OT plus 1 through capital T, comma ST plus 1 given STAT. And then we just have the remaining optimality term at the current time step given the current state in action, right? So we can take this thing and we can factorize it as a product of 3 terms by exploiting the conditional independence of future optimality given future state. Does anybody have any questions about this factorization? OK, good. So now let's look at these 3 terms. This term we know. This is our exponential reward. We know it up to a constant. So that's good. This term, this is our dynamics. We'll eventually actually derive model-free algorithms that can do this, but for now, let's just assume that we know the dynamics, right? So this is all good. And then we're just left with this first term, which is a little bit harder. And it turns out that this first term we can derive as following. Just like before, we can put in a new variable into this probability, and what we'll put in is AT plus 1. So we'll insert AT plus 1, and we'll factorize. And we'll factorize like this. We'll factorize into the probability of all the future optimality given the next state and the next action times the probability of the next action given the next state, right? Because if we multiply these together, we get P of O t plus 1 through t, comma, AT plus 1 given ST plus 1. So we're just marginalizing out the next action. This term is easy. This term is actually just the next backward message. This is literally the definition of beta ST plus 1, comma, AT plus 1. And then there's this funny term here, this probability of AT plus 1 given ST plus 1. The important thing about this term is that it is not conditional on optimality. So this is not a policy. This is just your prior probability of taking an action in a given state. This is a little bit weird, because this is saying, like, if you're not trying to accomplish anything in particular, what's your probability of taking an action? It turns out that we can play some games with how we choose this term depending on how we define our problem. And I'll talk about that a little bit later. But for now, let's just say that all actions are equally likely. So if you're not trying to do anything in particular, you're equally likely to take all actions. That's just an assumption that we'll make. And then later on, we'll actually unpack what this assumption really means. But for now, let's just say, if you're not trying to accomplish anything, all actions are equally likely, and therefore, this is a uniform distribution. And if it is a uniform distribution, then we can ignore it up to a constant. So we can just cross it out. So then, what we're left with is that we can get this thing just by integrating over the backward message just by integrating the action over the backward message. So it's just a marginalization operation. So then that tells us what the algorithm should be for computing these backward messages. For all the time steps, from the second to last one to the first one. Remember, at the last one, we already know the backward message. That's just the exponential reward. But the second to last to the first, we're going to compute beta as the probability of optimality at that step times the expectation over the next state of the state-only backward message, where the state-only backward message is obtained by taking an expectation with respect to the action. So we're going to just alternate these two steps, push the message backwards, push the state-only message backwards through the dynamics, and then push the action out of it to get the state backward message. So this step implements this integral, and this step implements this integral. OK, so that was kind of a lot of math, but does anybody have any questions about this? Yes?
So do you have to have the dynamic, like, so when you calculate the integral, you know, against the dynamics?
This one.
Yeah, I guess you would need to know, like, sort of in closed form, like st plus 1 equals st.
Yeah. Right, so the way that I wrote it out here, you actually have to know this thing to integrate it out. What we'll see later is that just like in model-free reinforcement learning, we can sample. That's going to be the magic, is that we'll just draw samples from the dynamics.
That's good,
yeah. Yes?
Can you say once again why we cannot view the crossed-out term as a policy?
Because it's not conditional on optimality. So this is just saying, what's your probability of taking an action given a state according to the laws of physics? And the laws of physics, if your actions are, let's say, you know, you're driving the car and you're turning the steering wheel, the laws of physics don't tell you about how you're allowed or not allowed to turn the steering wheel. You can turn however the heck you want. If you're not trying to accomplish anything in particular, who knows how you're going to choose your actions? So this is part of the problem definition. We can actually choose non-uniform probabilities here, but it is not a policy. And it's not a policy because it's not conditioned on any goal. So it's not trying to do anything. Yes?
Can you explain again how you got from the integral of state to the integral of action?
This? Oh, I didn't go from this to this. This thing is just writing out what this term is equal to. So this thing is just this. OK. So let's take a closer look at this backward pass. So this backward pass is going to get, now here's where things are going to get a little interesting. OK, I intentionally wrote it out like this because we're going to see some kind of cool transformation on this. I wrote it out in two steps. The first step is you push these state backward messages back one time step through the dynamics. And the second step is you take out the action by integrating over it to get a state-only backward message. Right? So everybody is good with these two things, right? OK, so now here's the cool part. Let's define v of s to be the log of the beta of s. And let's define q of s comma a to be the log of beta of s comma a. And let's just plug these in and see what happens. So let's look at this line first. Here we have beta of s and beta of s comma a, so mentally substitute in the log. And in log space, this just becomes, if you take the log of both sides, you get v of s is equal to the log of the integral of the exponential of q. So the way I got this is I just took the log of both sides, and I substitute exponential of q for this thing. And then I took out the expectation and put in an integral. OK? And now this is kind of cool. If SQ gets bigger and bigger, this quantity starts looking more and more like a max, right? Because the integral of exponentials is dominated by the term with the biggest exponent. So if the q's are really, really big, this integral of the exponentials of q, when you take the log of it, is very, very close to the max over the q's. If there's like one q that dominates everybody else, that's the one that's going to dominate this log integral of x. In fact, this phenomenon is so strong, this thing is sometimes referred to as a soft max. Not to be confused with the soft max that we use in deep learning. This is a soft max, meaning that it's a softening of the max operator. So as the q's get bigger and bigger, this log integral of x becomes dominated by the largest q. So that means that you can kind of say that this is a kind of relaxation of the max. And this equation, of course, you should all recognize, because this is how we've defined the value function for when we compute optimal value functions. So when we do, for example, LQR, when we go from the back to the front, we're computing our v's by maximizing q. When we do value iteration, we're computing our v's by maximizing q. So this looks an awful lot like reinforcement learning or optimal control. Let's look at the first term. Same thing, we're going to substitute the logs in there. When we substitute the logs in there, we get something a little funny. So when we take the log of this term, that's of course the reward up to a constant. When we and this term, this becomes the log expectation of the exponential of the next value. Okay, this is not quite right. Something here feels a little bit weird. If you remember the value iteration algorithm, the value iteration algorithm sets the Q to be the reward plus some discount, don't worry about the discount for now, of the expectation of the next v. And here we have the log of the expectation of the exponential of the next v. That's not quite the same. If your dynamics are deterministic, then it is exactly the same. If your dynamics are deterministic, this expectation vanishes and you get a log of an exp, which cancels out. So under deterministic dynamics, this is exactly identical to value iteration, this step. But under stochastic dynamics, it's not. What does it mean under stochastic dynamics? So this is the deterministic version. Under stochastic dynamics, this is kind of you can think of it almost as an optimistic transition. So if there is one v that's a little bit bigger than the rest, that bigger v will dominate this log expectation exp. So it's kind of optimistic. Like in general, this thing will be bigger than that thing. If you take the log expectation of exp, you get a bigger value in general than the expectation of the original quantity. That's maybe not quite right. Like one of the implications of this is that if you're driving your car on the edge of a cliff, and occasionally the car falls off the cliff, you get a very big negative reward. That's going to give you a very bad Q value up here, but it won't actually give you a very bad Q value over here because that small term will vanish, and the big term where you actually stay on the road is going to dominate this thing. So it's kind of optimistic. It's saying, I'm going to be optimistic with respect to my dynamics. Not usually a good idea, because it'll cause you to drive on the edge of the cliff. It turns out that there is a modification to this framework of control as inference that's sometimes called maximal causal entropy that corrects this little deficiency. Theoretically, this framework is a little bit complex, so I won't get into it in this lecture. But it basically explains how you can turn this term into the more conventional one that you expect, where you actually take the expectation over the next value. And if you want to learn more about how you can go from graphical models to this kind of update, check out this paper, Modeling Interaction by the Principle of Maximal Causal Entropy. So short version, if we go through the inference framework, we get an update equation that looks an awful lot like value iteration with a softened max and this somewhat weird optimistic transition. If the dynamics are deterministic, the optimistic transition is just your regular transition. But if they're stochastic, then this can have some weird effects. It can cause you to act optimistically in the face of uncertainty. If you don't want that, check out this and just change your equation to this. OK, does anybody have any questions about this? OK. So quick summary of the backward pass. So your backward message, this is the probability that we can be optimal at steps t through capital T, given that we take action A in state S. And that sounds an awful lot like a Q function. You can compute it recursively from the last step to the first step by taking these two steps in alternating fashion. And the log of the backward message is sort of Q function-like. So it looks a lot like a Q function. If you take the logs of everything, the updates look like value iteration with the softened max and this additional detail that we have to remember about the dynamics. So to do that, you just let your Q be the log of the state action backward message, and you let your V be the log of the state backward message. Okay, so that's backward message passing. Looks a lot like value iteration. Now let's revisit the action prior, and let's talk about it a little bit more. So remember this thing that we did where we said that we'll just assume that if we don't condition on optimality, then P of A given S is just going to be some constant. It's going to be uniform. And that was good enough for us. Let's think about what happens when it's not uniform. So what if the action prior is not uniform? What if we say, OK, well, maybe P of A given S is like a Gaussian standard at 0 if you have continuous actions. Why not? That seems reasonable. If you look at the equation for the value, it's the log of the integral of the Q. And now if this log P is not, like if P is not a constant, then you have to leave it in here. You get this log P in there, right? So this is the softmax that we saw before. And your Q is the reward plus the expectation for the next value, or the log expectation exponential if you want to use the optimistic version, right? So the Q looks something like this. So now, if we have this log P, we can define a new Q, Q tilde, that is R plus log P plus expectation of the next value, and then your V is back to being the softmax. So another way to look at it is if your log P if the P is not a constant, which means the log P does need to be in that equation, you can still view the V as a softmax just over this Q tilde. Does anybody have any concerns about this, or does this make sense to everyone? Yeah? Yes?
Why is it log P rather than just P?
Oh, because I put it in the exponent. So this is a silly thing to do. I just said exponent of log, just so I could do this thing additively in log space. So when you do it additively in log space, you can see that you're still doing a softmax. It's just you now have this Q tilde, where all you did is you took your reward and you added the log P to it. So that means that you can always fold the action prior into the reward. And the uniform action prior can actually be assumed without any loss of generality, because you can say, well, if you want a non-uniform action prior, that just means you have a different reward. So you just don't worry about the action prior, just put the thing in the reward. And if you really want a non-uniform action prior, like if let's say you have a Gaussian action prior, that just corresponds to a squared, a quadratic term on your reward that's quadratic in the action. That's perfectly fine. So this is why we don't have to worry about this P of A given S, because it can always be exchanged with a term in the reward function, and in the end, it actually just doesn't matter. So log P A given S is like, it's reward-like. We can put it into the reward if we want to. OK? Does anybody have any more questions about the action prior? OK. So hopefully that resolves all of the action prior related concerns. All right. Let's talk about the second inference problem, the problem of computing a policy, the probability of A given S, comma, optimality from step 1 through capital T. So this is the probability of taking an action if you're in some state and you know that you want to be optimal everywhere, approximately optimal. OK, so that's the policy. P of A given S, comma, O 1 through T, that's your pi. And you can, since the optimality is conditionally independent of past optimality given the state, you can change this O 1 through T to be O little t through capital T, right? We can ignore all the past optimality because of conditional dependence due to the state. That simplifies things a little. And now what we can do is we can write it out using the definition of conditional distributions, where we put the state in the joint. So we say probability of action comma state given optimality divided by the probability of state given optimality. So that we're also allowed to do. And now what we'll do is we'll take both the top and bottom here. This is a little bit more complex. We're going to actually apply Bayes' rule to both the top and the bottom. So remember, Bayes' rule says that P of A given B is P of B given A times P of A divided by P of B, right? So, and we just did it to both the top and the bottom. So that's why you have like a little division operator in both the top and bottom. Now, both the top and bottom are actually divided by the same thing, so that can be canceled out. So we're just left with the top parts of Bayes' rule, right? And now we can take these two things. There's a product in the top and product in the bottom, and we can break them up so we just have the first ratio times the second ratio. So I just took these two terms, put them here, took these two terms, and put them there, OK? And now, remember that the backward message is the probability of O little t through capital T given S and A, and the state backward message is the same thing but given only S, right? So those we had from step 1. And now look at what we've got here. We got the state action backward message, the state backward message, and this thing is just A given S. This is just our action prior, which we've decided is going to be uniform. So P of A comma S divided by P of S, that's P of A given S, action prior, it's uniform, and we're just left with a ratio of the backward messages. That's very convenient because we already know what the backward messages are. We already have our backward algorithm for computing them. So that means that our policy, pi of A given S, which was P of A given S, comma, O 1 through capital T, is just the ratio of the state action backward message and the state backward message. So if we have those things, if we got them in our backward pass, we just take that ratio and that gives us our action probabilities if we're being approximately optimal. So let's summarize what we've got here. we had our backward pass, which does this, which computes this Q and V, and this is the causal entropy version. This is the one that takes the expectation. You can also have the optimistic version. And we said that our pi is beta SA divided by beta S. We know what those are in log space, right? That's the V and the Q. So that means that our pi is the exponential of the Q minus the V, which is just the exponential of the advantage. That makes a lot of sense. That's saying that if you have an advantage function, which, just like before, tells us how much better is a given action than the average action, you want to take actions with probability proportional to the exponential of how advantageous they are. And the most advantageous action is the most probable, and they fall off from there. So that's actually awfully convenient. The value function normalizes the Q function, and the exponential of the advantage is your policy. There are a few variants of this framework. You can have a discounted version of stochastic optimal control. So all that means is you can put in the discount. The same interpretation that we had before for the discount, this depth probability, that still holds, and all is good, and you can have a discount. You can explicitly add in a temperature. I don't usually talk about, I'm not going to talk about this in great detail, because when you put in a temperature like this, that turns out to just correspond to multiplying your reward by a constant, right? Because these Q's and the V's, they're going to be, their magnitude depends very strongly on the magnitude of the reward. So if you take the reward and you multiply by like a million, all the Q's and the V's get a million times bigger, and the corresponding distribution gets a million times sharper. But if you want an explicit variable to control that, you can put in this alpha in front when you take the soft max, and that'll also have that effect. In particular, as alpha goes to 0, then this softmax approaches a hard max, because as alpha goes to 0, these terms blow up, which means that the largest Q dominates the log integral exp, and it looks more like a hard max, which looks more like standard value iteration. So if you put in the temperature, that allows you to actually smoothly interpolate from the soft optimal framework and the more traditional hard optimal framework that we learned about when we learned about value iteration. OK, so summary of the policy computation. With the temperature, you put in the alpha, you get this thing. So that means that as alpha goes to 0, policy becomes deterministic, max becomes deterministic, and you recover the standard normal hard notion of optimality that we had before. It has a very natural interpretation. Better actions are more probable according to the advantage. You have random tie breaking. So if you have two actions that have exactly the same advantage, you're equally likely to take both of them. So you don't have to worry about any tie breaking. And it's analogous to Boltzmann exploration. So those of you that remember when we talked about Q-learning, we talked about this thing called Boltzmann exploration, where you take actions in proportion to their advantage. This is a way that you can derive the mathematical justification for Boltzmann exploration. It approaches the greedy policy, the deterministic policy, as the temperature decreases. So if you drive the temperature down to 0, you recover the standard hard optimal policy that always takes the very best action. OK, does anybody have any questions about the policy computation? OK. So now let's talk about the third and final inference question, which is not as important if you want to compute policies, but it will become very important if we want to do inverse reinforcement learning, and that's the forward message. So we can go backwards, we can also go forward, and a forward message is this. The forward message is the probability of being in a particular state given that you are optimal at all the time steps until now. So if you don't care about the future, you've been optimal up until now, what's your probability of landing in a particular state? This seems a little peculiar, but we'll actually see shortly why there's a very nice symmetry between forward messages and backward messages. But first, let's actually derive the forward messages. So the forward message at the first time step, that's just your probability of starting in a particular state. Usually we assume that this is known. So usually we assume that nature tells you where to start. You don't get to choose where to start. So we just care about all the steps from 2 until the end. So let's do the same thing that we did with the backward messages. Let's add some more variables in here, and let's marginalize them out. And specifically, the variables that I'll put in are going to be the previous state and the previous action. And when you put in the previous state and the previous action, you get a big joint, and then you can factorize that joint into a product of terms. And here, I skipped a step, so I jumped directly to the factorization. So you can take my word for it that if you multiply all these things together, you're going to get P of st, comma st minus 1, comma at minus 1, given O of 1 through t minus 1. And what are these terms? Well, this thing we all know. This is our dynamics. This thing is our previous backward message. So this is just the probability of being in a previous state given all the optimality variables before that. So this thing we also know. So we're just left with this middle term that's a little bit complicated. The probability of the action at t minus 1 given the state at t minus 1, comma the optimality at t minus 1. And this thing, we can, again, do the Bayes rule thing to it, and we can get the probability of optimality given st minus 1, at minus 1. This thing we know, this is just the exponential reward, times the action prior divided by p of ot minus 1 given st minus 1. This is some normalizer, right? So we don't care about this thing because we can the bottom part because we can just always renormalize this thing. So it's just the probability of exponential reward and the action prior, which is constant. All right, so this is how we just plug this thing in here, and we can compute our forward message. So now, if we can compute the forward message, what if we then want the probability of a state given optimality at all the time steps? Turns out that it's actually very simple once we have the forward messages and the backward messages. So p of st given O1 through capital T, that's just equal, again, we're going to do the definition of conditional distributions. We put the joint on the top and some denominator that we don't care about. On the top, this thing we can factorize it as probability of optimality given the state times probability of current to future optimality given the state times the probability of the current state and all the past optimality. So I've just broken up the optimality between the future and the past by using the conditional dependence of optimality given the state. So this part, this is just the backward message, the state backward message at time step t. And the second part, I can break it up again because I can break it up as the probability of st given this part times the probability of this part, right? And that probability is independent of the state, so I just have the forward message. So that's what I did here. I took probability of s given O times the probability of O, and I'm ignoring the denominator because I just want it to be proportional. So I have beta times this thing times something that doesn't depend on s. And this thing is just the forward message. And this thing doesn't depend on s, so I can ignore it up to a constant of proportionality. So I'm left with just beta times alpha. So if you compute the backward messages, you compute the forward messages, you just multiply them together, and you get the probability of being in a particular state given, given that you're optimal everywhere. And those of you that are familiar with inference and hidden Markov models or Kalman smoothers, you'll probably recognize this as exactly the same thing as what you do in HMMs or Kalman smoothers. You just compute your backward message, compute your forward message, multiply, and renormalize. And that gives you your state marginals. Let's get into the intuition of what this actually means a little bit more. There's a nice kind of graphical way of illustrating this that helps me think about it a little bit. So let's go back to the monkey that's trying to reach some dot. Let's say this is the point that the monkey's trying to reach. This is the point where it starts, and it wants to go to the target, but it's going to have some stochasticity due to the fact that it's only approximately optimal. You can think of the backward messages, if the reward of the monkey only depends on reaching this goal, you can think of the backward messages roughly as being kind of an indicator of reachability. So if you have a big value in your state backward message, that means that from all these points, you can reach the destination. And as you go further back in time, there are more points from which you can reach the destination because you have more time to get there. So you can think of this as kind of a cone projecting backward in time, if your only goal in life is to reach this point, right? So the further back in time you go, the wider this cone becomes. So states with high probability of reaching the goal, you can kind of think of them as being inside this yellow thing. The forward messages are basically just the same thing, but in reverse. So the forward messages tell you how likely are you to reach certain states if you started here and are acting with good optimality up until now. So this is sort of the states that you can reach if you start here and don't do anything stupid. So then it makes perfect sense that if you want to figure out how likely are you to be in a particular state at any given time, given that you're trying to reach this goal, you just multiply these two things. You basically take their intersection. So the blue thing is states with high probability of being reached from the initial state with high reward. The yellow states are states from which you can reach the goal with high reward. So if you multiply them together, you're sort of taking their intersection, and these are your state marginals. So that's kind of a graphical illustration of what it means to multiply these backward and forward messages. You can think of a cone projecting backward from the target, a cone projecting forward from the initial state, and you're just taking their intersection. Does anybody have any questions about this? Yes?
So what determines how large the fan is?
So it's determined by the reward function and the dynamics. So if your reward function is just like 1 if you reach this thing and 0 if you didn't, So there's nothing soft. It's just a very hard cliff. And your dynamics are also maybe deterministic. They just tell you, if you're over here, you can go fast enough to reach the target. And if you're over here, then you can't. Then these things will actually look like a step function. But of course, in reality, maybe your reward function is some soft thing, and your dynamics are stochastic. So then these will look like softened out cones. Yes?
So if you have continuous distributions, do all of the messages stay like nice and easily representable, or do you have to distribute?
Oh, absolutely not.
Okay.
So this is exactly the same issue as with Q functions. And then there's actually a reason why we call that thing log Q, is that in the same way that a Q function can get arbitrarily complex, these messages can get absolutely fiendishly complex. Yeah. OK. Now, interestingly, this is maybe a little bit of a side note, but it's kind of interesting to note. People have actually done experiments like this where they ask, for example, monkeys or humans to reach from a particular point to the other, and then they actually measure their state distributions at any given time step. So this is a picture from a paper by Lee and Todorov from 2006, where they actually have a human subject who's asked to reach different points, and then they record the variance of the position of their end effector, of their hand, at different points in time, and they see that it actually looks an awful lot like this. So these are plots of the end effector variance. So you can see they go up partway through the path, and then they go down. So the largest variance is halfway through, which makes sense. If you're trying to reach some point, then the place in time where it least matters where you are is in the middle, because that's where you're furthest from the start and furthest from the end. So yeah, this picture is a cute cartoon, but it actually real human subjects data actually follows a similar pattern for reaching motions at least. OK, so in summary, we have a probabilistic graphical model for optimal control, and it's this model. Control can be done by using inference in this model, which looks very similar to hidden Markov models and extended Kalman filters. It's also very similar to dynamic programming and value iteration, but softened. So you can recover regular value iteration if you have a temperature and you drive that temperature down to 0. But for non-zero temperatures, it's a kind of a softened version of value iteration. We can derive, actually, many of the same reinforcement learning algorithms that we covered up until now in this framework of soft optimality or control as inference. So we can recover, for example, Q-learning. How do we recover Q-learning? Well, in standard Q-learning, this is the update that you make. So this is the reward. This is the, so the reward plus the next value minus the current Q, and you multiply that by the gradient of the Q. So that's the standard Q-learning rule that we learned about. The target value is given by the max over the Q at the next time step. That's Q-learning. And then with soft optimality, update equation is exactly the same, except that now the target value is a soft max instead of a hard max. And that's it. So instead of maximizing over the next action, you integrate over the next action. And that gives you Q-learning under soft optimality. And that's the only change. And then the policy needs to, you're no longer free to choose any policy you want. You should actually use this exponential advantage policy. So you have to use Boltzmann exploration for this to make sense. So the resulting algorithm, exactly the same algorithm as we saw before, except that now this max becomes a soft max. And the other details for number 1, you can do the off-policy thing, but if you want to do on-policy, you should take actions according to this instead of according to the hard max. So take actions according to the soft max and compute your target values according to the soft max. And you're actually implementing this inference procedure in a Q-learning algorithm. You can do policy gradients with soft optimality also. So if you want to do policy gradients with soft optimality, it turns out that the policy that is equal to the exponential of the Q minus V, it actually optimizes the expectation of the reward plus the entropy of the policy. The derivation for this is a little bit more involved, but I can provide a little bit of intuition for why this is the case. So the intuition is this, that if your policy is proportional to the exponential of the Q, then it somehow minimizes a divergence measure against the exponential Q distribution. So if you're minimizing a divergence measure against the exponential Q distribution, then the way that you get that, you could write out the KL divergence. It's just the expectation of the Q minus the entropy. So the definition of the KL divergence has this entropy term in there, and that's actually where it comes from up here. This is not a formal proof, this kind of hand-wavy intuition, but if you want the more formal derivation, check out this paper. So the short version here is that you can implement soft optimality in a policy gradient or policy optimization framework, and all you do to do that is you change your objective to be not just expected reward, but expected reward plus entropy. And there's a reasonable intuition for, like a functional intuition for this also, which is that, you know, if you end up with this policy that is proportional to exponential a, there needs to be some kind of pressure that keeps it from collapsing into a deterministic policy, and that pressure is the entropy term. So this is often referred to as an entropy regularized policy gradient, and this trick of adding this entropy here is often used to prevent premature collapse of the entropy. This is particularly important in continuous action spaces, because if you use something like a Gaussian distribution in continuous action spaces, you might find that your policy gradient algorithm really wants to reduce the variance of your policy. Because reducing the variance of your policy is often a very good way to locally increase your reward. But it can get you really stuck, because once the entropy of your policy falls to a very small number, the policy basically does the same thing over and over again, and it stops improving. So as a very practical trick, just adding this term to your objective in a policy gradient algorithm could improve your exploration a little bit and keep it from getting stuck prematurely. But the more in-depth mathematical explanation when you do that is that you're actually switching to this framework of soft optimality. And it turns out there's actually a very close connection between policy gradient and softened Q-learning, which is explored in these two papers, one by Thomas Hornoy and the other by John Schulman. So I'll actually go, at a very high level, I'll go through this connection. I won't derive it very formally, but I'll sort of show you some of the equations to give you a preview of why Q-learning and policy gradient are actually very closely connected in this soft optimality framework. So this is our entropy regularized policy gradient objective. Maximize expected reward and maximize entropy. And there's an expectation here. This is the reward expectation under pi of s comma a, entropy expectation under pi of s. Now, this entropy, just from the definition, it's expectation under pi of a given s of negative log pi a given s. So you have an expectation over pi of s. Inside is an expectation over pi of a given s, so you can combine them together. And that means that you can rewrite this objective like this, expectation under pi of s comma a of the reward minus log pi. Makes sense. So then you can compute its gradient, just the same way that we computed the policy gradient before. You just have a modified reward function. So when you compute its gradient, OK, this is a little bit long, but let me walk you through this. The first part is you just differentiate through the p that's inside the expectation. So just treat this whole thing as a reward. And if you do that, you get this stuff, right? So you get, and I intentionally wrote it out in sort of a peculiar form. These things, this is the sum of the reward from time step t to capital T, and I just broke it up to put the t here and the sums of all the future rewards in here. And we'll see why this is good later on. So these are just the rewards. And these are the sums of the log pi's. Again, the sums of all the future log pi's and the current log pi. So these are just this modified reward function. Now there's a second term in the gradient which comes from the fact that this log pi also depends on your policy parameters. So if you take the derivative of this thing, you just get the gradient of log pi. So gradient of log pi times -1. So that's where this -1 comes from. Now, if you remember, if you have a policy gradient and you have a constant inside this, the coefficient for grad log pi, that constant disappears when you have a baseline. So it turns out that the gradient of this term actually just doesn't matter. It ends up being a -1, and when you put a baseline in there, it just kills that term. So you don't even have to worry about it. You can just pretend that this thing is a modified reward function, and that's it. OK, so now that we wrote it out like this, let's start grouping these terms together a little bit. So the -1, that just comes from here. We can ignore it due to the baseline. This thing, this is a Q function style term, right? See, it's a sum of future rewards. So we can treat this as approximately being the Q function at the next state in action. I told you this is a little hand-wavy, so bear with me on this. So now recall that your log pi is Q minus V. So let's plug that in. Now the grad log pi becomes a grad Q minus grad V. This is the Q that we got from here. And this minus log pi becomes negative Q plus V, right? Negative log pi. This thing doesn't depend on action, so we can kill it if we put in the right baseline. So we can just ignore this thing because we can put in a baseline that just eliminates it. In Q-learning, what does our gradient look like? This is the soft Q-learning gradient. Reward plus the softmax of the next Q minus Q. OK, so now just look at these two things. They look kind of similar. And if you read the two papers on the previous slide, they'll describe more formally why they're actually similar. But for now, we'll do sort of what is it, hand-wavy proof by observation. We look at them and we say they look kind of similar. But it's not actually an accident, and the two papers on the previous slide dig into this a little bit more. So the main differences here, there's a negative sign because Q-learning is gradient descent, whereas the policy gradient is a gradient ascent. So that doesn't matter. That's just a sign. This is off. So Q-learning is off policy. So there's a softmax. If you're on policy, you can just use the Q. You can actually derive an on-policy version of Q-learning also. It's called SARSA. So if you have SARSA, then this term looks exactly the same as this term. But for off-policy Q-learning, there's a softmax. So that's a difference. And then the only other difference is that you have a grad Q here and you have a grad Q minus V here. So there's a little difference in how you compute the gradient. But other than these things, they're basically doing the same thing. So they're both doing this gradient procedure where you have an R plus Q inside, and you have a grad Q with maybe some correction on the outside. So if you want to learn more about this connection between policy gradient and Q-learning, take a look at the two papers that I had on the previous slide, but this is a little preview of this that sort of shows that actually, in the framework of soft optimality or control as inference, Q-learning and policy gradient actually do fairly similar things. OK, so just to wrap up this part, some of the benefits of soft optimality, they can improve exploration to prevent this entropy collapse problem, especially if you're doing policy gradients. This one we'll see next when I talk about an example algorithm in the literature. It can be easier to actually fine-tune policies for specific tasks if they were trained with soft optimality, and we'll see that shortly. It provides a principal approach to break ties. So if you have two actions with the same advantage, they'll be equally likely. And you actually get better robustness. This one is a little bit non-obvious, but the intuition behind it is that if you have a policy that is trained to maximize entropy, that it visits a variety of different states, it'll actually be more robust to variations in your model because it essentially has learned to be successful under different conditions. So if it gets perturbed into a different condition, it's more likely to know what to do there. And there's a more formal way to study this robustness improvement also. So some of the work by Brian Ziebart has looked into this. And it can reduce to regular classical hard optimality as the reward magnitude increases. So if you put a temperature, you drive that temperature to 0, you recover standard hard optimality. And as we'll learn next week, it's actually good for modeling human behavior for inverse reinforcement learning. So I'll skip this part because we're running a little short on time. And let me tell you a little bit about, in the last few minutes of the class, let me tell you about a particular paper that actually implements the Q-learning version of this soft optimality procedure to actually derive a practically useful reinforcement learning algorithm. So one of the ways that we can illustrate, so the kind of the challenge that this paper is aiming to solve, we can illustrate it with an example. So this is a video that I think many of you saw before in the policy gradient lecture. This is a policy gradient algorithm learning how to run. This is very nice because the guy learns how to run. But if you run that same algorithm a second time, actually pretty much the same algorithm, just with slightly different hyperparameters, you get a very different run. And both of these runs actually have fairly high reward. It's not the same. This one is a little bit better. But the point is that just through a small difference in exploration, the random exploration that the learner took early on in the training process, actually arrived at a very different solution. And it makes a lot of sense that this would happen because reinforcement learning, once it finds a region that has high reward, it reinforces it. It sends more probability mass there. So it's actually quite prone to pick up on these local optima. We can illustrate this with a little kind of, in a simpler setting where it's a bit easier for us to really get a feel for this problem. In this setting, there's a little quadruped robot, and it wants to get to this blue square. And the reward function tells it how far away it is from the blue square. So the closer it is, the more it's rewarded. And when it actually gets to the blue square, then it's very happy. That's its ultimate goal in life. The trouble is that when it begins exploring, if it chooses the upper passage or the lower passage, they both initially seem equally rewarding. So it only discovers that the lower passage is good if it explores both of them and then gets to the end. So if it accidentally gets a little further up at the top, it might decide, well, the top passage is pretty good because I've gotten a little bit further there, so I'll just keep going there, and I'll just forget about that bottom passage because it doesn't seem to be working out for me, just due to random chance. So the right strategy here is to track both of these hypotheses, to study all of the options that are available to you until you find the one that's actually better. And it's pretty obvious in this setting down here, but that's actually the same problem up here, that if this little humanoid had explored all the different gates before committing to one that seemed the most promising, then it would have discovered whatever was the right gate to execute. So one of the ways that you can actually do this is with this framework of soft optimality that I described. So you can actually construct stochastic energy-based policies. This is some work by Thomas Harnoy and Haran Tang. And what they did is they actually implemented a Q-learning-based algorithm with soft optimality. So it's going to learn this Q function that we've already learned about. And in a conventional Q-learning algorithm, if you're doing something like epsilon greedy, what you would do is you would pick the tallest hill. Like if you're standing right here and you have two peaks in your Q function, one to go up and one to go down, you would pick the tallest hill, but then with some epsilon probability, you'd pick a random action. If you want to explore both hypotheses, then what you want to do is you want to commit your probability mass in proportion to the size of the Qs. So maybe you want this. This is what soft optimality tells us to do. Make the policy proportional to exponential Q. And the constant of proportionality there is actually just the V, as we learned. So this just means make it equal to the exponential advantage. So this is all the stuff that we've already covered. You can do the softmax. And then the question is, how do you actually implement this in practice? If you have continuous actions, OK, you can have a neural network that takes in the state and action and gives you the Q value. That part is straightforward. But you need some way to sample from this policy, from this pi a given s, that's proportional to these exponential Qs. And that's actually a difficult sampling problem because this Q function might be really complicated. So Q-learning tells you how to learn the Q function. And yeah, you use the soft target value. And then the question is, how do you sample from this pi? That's the part that gets a little tricky. So there are a number of things you can do. And they all have this flavor of borrowing ideas from approximate inference. So this is where the connection between inference and control really becomes valuable. And if we look at the world of approximate inference, the world of approximate inference will tell us that this thing is something called an energy-based model, where the Q part is the energy, and the difficult part of training energy-based models is the normalization. So that's why it's a little hard to sample from these things. So we can look at the kind of techniques that people have used to approximately sample from energy-based models. There are a number of different options available, but the option that was actually used in this paper is to train a network, train an approximate sampling network using a variational lower bound. And that approximate sampling network takes in a state and a sample of noise. This maybe is like spherical Gaussian noise, and outputs an action such that this action is an unbiased sample from the exponential Q distribution. So now you need an algorithm that will actually train this thing. But those of you that remember the imitation learning lecture will recognize this as an instance of an implicit density model. So when I talked about implicit density models in imitation learning, this is the kind of model I was talking about. So there are a few ways to train these kind of models to produce unbiased samples from some target distribution. The particular one that's used in this paper is something called Stein variational gradient descent, which is a gradient-based method for training this network. You can intuitively think of it as computing gradients through the Q function, pushing them into this thing, and then adding an additional term that says that for different noise values, the samples should be far apart. And you can actually choose that repulsive term in such a way that you train this network to produce unbiased samples from the exponential Q. So the Stein variational gradient descent method, and this is where the connection between inference and control comes in, it was originally proposed for approximate inference with these kinds of models for the purpose of generating images. So this is like, those of you that are familiar with GANs, generative adversarial networks, kind of very similar idea. Generate images where you can build an energy for the discriminator, and then you have this kind of generator that takes in a noise. But because of the connection between inference and control, we can actually take the same method and apply it to train these networks to produce approximate sampling distributions for our policy. So this is kind of a higher level overview of this paper, but if you want to learn more about it, you can see the details in the paper itself. What I want to tell you about in the last few minutes is some of the ways in which this method can be used and what some of the potential benefits are. This is not necessarily a better way to train policies in every situation. So it might help you address this exploration problem, but there's nothing inherently just better about it. But there are a few cases where it can be very useful. So here's one interesting case. If you have an underspecified reward function, a conventional reinforcement learning, like underspecified in the sense that, for example, you just tell this little quadruped, run in any direction. So you just tell, you get a reward for running fast, but we don't care what direction you run in. A standard reinforcement learning algorithm will break the tie in an arbitrary way. So it'll pick a direction and it'll run in that direction. Because of the entropy maximization in the controls inference framework, a solution obtained with any kind of soft algorithm like soft Q-learning or entropy regularized policy gradient will actually maximize the randomness of the behavior, so it will actually choose to run in all possible directions. And you can actually see this in the video. So here on the left, I'm showing a video from a standard deterministic reinforcement learning algorithm. This is actually DDPG, where it just adds its usual exploration noise. So it's a unimodal policy with exploration noise. And on the right, I'm showing the examples of samples from the soft Q-learning policy. And there they are. So you can see that this guy is biased to run in a particular direction. Eventually, the random noise takes over and just goes all over the place. But this one actually, as soon as it starts, let me go back and play that again. As soon as it starts, it actually immediately runs in all possible directions. And the more samples you generate, the more directions you'll cover. So why is this useful? OK, it's seemingly kind of a useless thing. We just trained this little spider-like thing to run in random directions. But it can be very useful if we want to then specialize this behavior to particular tasks. So if we want to pre-train over here, and then maybe later on, we want this guy to very quickly learn a new skill. Like we want it very quickly to learn how to run down a hallway. If we initialize with a policy that already knows how to run in all possible directions, it should be much quicker for it to learn how to run in a particular direction. If we initialize with this policy has learned to run in a particular arbitrary direction, so it's going to take a lot longer to specialize. So this is the video of the specialization process, and this is the first iteration, the first epoch. You can see they all kind of do arbitrary things. But as learning progresses, here we have the 100th epoch. And by the 100th epoch, the two policies that are pre-trained, they're getting a little bit further. And you'll actually see that this one ends up getting quite a bit further in the 100th epoch. And then as learning progresses, this one actually ends up making it all the way down the hallway quite a bit sooner because it has this good initialization. And we can do a quantitative evaluation of this too. So the blue lines, these are different shaped mazes. The blue lines show the policy that was initialized with this entropy maximization. The green line is initialized with a deterministic RL algorithm, and the orange is randomly initialized. So this is kind of an interesting benefit, that if we use the control as inference framework, we can actually train these policies that do a particular underspecified task essentially in all possible ways, because that's what they're optimizing for. And that can be useful for pre-training for subsequent fine-tuning, and it can also be useful for exploration. All right. There's quite a bit more work on maximum entropy policies and soft optimality. So if you're interested in learning more about this topic, there's some classic work by Salins and Hinton. This work looks at actually training what are called restricted Boltzmann machine models as energy-based policies. So this is sort of in some ways, a precursor to some of this maximum entropy work. So that if you want some classic work on the topic, that's a good thing to check out. There's some very recent work. This is out of Google, actually, called Bridging the Gap Between Value and Policy-Based Reinforcement Learning, that studies interesting off-policy algorithms that you can derive once you switch over to the inference framework. So if you're interested in off-policy algorithms, this is a good thing to read about. There's a pretty widely explored class of algorithms in robotics called relative entropy policy search algorithms that are derived from this framework of control as inference. So if you're interested in robotics tasks, this is a good thing to check out. And then there's a number of recent works in deep reinforcement learning that have looked at incorporating entropy terms as regularization to improve exploration for policy gradient and active critic style methods. So this is an example of one of those works if you want to learn more about that. And then, of course, the ones I mentioned previously, the connection between soft Q-learning and policy gradient, and the soft Q-learning for which I showed the videos. So these are all things that you guys can read about if you want to learn more about this topic. Some more kind of theoretical suggested readings. There are actually a number of papers that independently propose the control as inference framework. One of these papers that you can read about is this one by Emmanuel Todorov. This is an interesting paper that sort of serves as a short and readily accessible primer on the duality between inference and control, and also discusses a little bit more some of the historical origins of this framework. This is some work by Bert Kaplan, who's another researcher that has studied this topic in detail. This is the work by Brian Ziebart. I would highly recommend this if you want to learn more about the theory, especially the maximal causal entropy framework. This is a paper that introduces a temporal difference learning style algorithm, kind of a precursor to the soft Q-learning work that I showed. This is the soft Q-learning paper. This is the bridging the gap paper that I had on the previous slide. And then this is another paper that studies the equivalence between policy gradients and soft Q learning. So if you want to learn more, these are also good foundational papers to read. Does anybody have any questions about anything that I covered today? Yes?
I'll ask you offline.
OK. Well, make sure that you guys turn in your homework 3 by midnight tonight, and project proposals next Monday. So I'll see you all next week.
So, I have actually a very interesting lecture. I have a few questions. The general sort of like inference